Okay everyone, so we're going to have a look at the question that we had a look at last week that went a bit wrong. Now I found the problem, there's a few problems actually, and we can work out this together now. So we're going to have a look at this problem here, question 2. So it's a lift, and let's just draw this so we can get a feel for what's actually happening. 1200 kilos and 1000 kilos hanging on either end of a drum which has a moment of inertia of 500 kilos per meter squared, kilometer squared, and a radius of 1 meter. Now the radius of 1 meter does make things nice and simple for us, because what it means is our torque is always going to be equal to our force. So on this side we've got 1200, and on this side we've got 1000. Obviously it's going to want to come this way naturally, because it's a higher force, but we've also got a force here wanting to resist movement in any direction of 500 kilogram meter squared, and that's our value I. So the first part of the question says work out, so this is part, is it A or I? Let me just have a look. I. The maximum and minimum force on the rope during this period. Now this is where I think there's been a mistake in the actual question, and we'll see this, and that's what threw us a little bit. So there are two tensions in the rope, this one and this one. Now obviously we've got a couple of things happening here. On both of these we've got the force of gravity, so let's take this one first, we'll call it T1, and the tension there in the force is going to be equal to, well, F equals ma, so just the force of gravity, 1200 times 9.81, but also there's another force, because the question says that it's accelerating for 2 meters per second. So that acceleration is going to, as we try and accelerate an object faster, it's going to want to resist that through inertia. So plus, it's going to have the 1200, put these in brackets, 1200 times 2 meters per second. And if we add all those together and type them in, 1200 times 9.81 plus 1200 times 2 meters per second gives us our force or tension of 14.72 newtons, and that's the tension in T1. We could have just as easily worked this out as saying 1200 times 11.81. We could have added those two accelerations together, gravity and the upward force. That would have given us the same answer. Now where we went wrong before was T2, which was here, because with T2 we just assumed it was gravity pulling down, and gravity pulling down is one of the tensions in that rope. So that's 1000 times 9.81. But we know as we fall we can experience weightlessness or lack of gravity. That's why when we see those planes that can simulate weightlessness of space, they're falling at a rate equal to gravity. So if this object here, this 1000 kilos, was dropping really, really fast, there'd be no tension in the rope because it'd be free fall down, there'd be no tension there. But in this case, it's accelerating down at 2 meters per second. So we could go and add that, do a separate one, but actually we can just take that away from there and say that this is now got an acceleration of 7.81 meters per second. That's the 9.81, take away the 2, which will give us the force on this rope, which is going to be 1000 times 7.81, which is 7,810 newtons. So that's the difference. They're the two tensions in the rope, maximum and minimum. We see them here, so these two are the answers. So then we move on to the next question. Now the next question is a bit easier because we've got the right answers in the bit above. So the applied torque to the drum during the acceleration period. Okay. Well, this works out easier now we've got our figures. So let's think about this as a free body diagram. Oops, not with the highlights up. So think about our free body. and we've got a couple of forces pulling either way. So we've got this force wanting to pull up, which is 7, 8, 10. We've got our 14 172, but we've also got inertia. The inertia effects anyway of this trying to accelerate this flywheel at this speed. Obviously it's quite a big flywheel, so in this case that's actually going to be, well, it's going to create a torque there, and we know that torque is equal to, so this was part 1, sorry, I'll draw a line across here, this is part 2. So torque is equal to I alpha. Well, because we've got 1 meter radius, then radians per second and meters per second are going to be the same, and so is acceleration. So in this case we've got 500 times our acceleration, which is 2. So our torque is 1000 Newton meters. Now what force is that creating? Well, it's 1 meter out from the center, the radius. So Newton meters and Newton's force on the rope are going to be the same in this case. So this force here, this torque force, is going to be another 1000 newtons. And now if we do the calculation of getting rid of these, taking them away, we do 14,172. Add 1000 because it's going in the same direction, and then take away 7810. Then we get 7362. And that will be Newton meters. This is, I'll call it TN, net torque. So that's the amount of force the motor in this object here has got to produce to accelerate this mass up here at 2 meters per second, overcoming the weight of both of these objects because they'll have inertia, and the angular inertia of the flywheel. It needs to supply 7,362 Newton meter torque in this direction there to actually achieve that. So that's that bit. What we didn't do before, we didn't take into account the inertia. Before we didn't use the 7,810. We had 9,810 because we didn't take into account the free fall. So next bit of the question. This is a bit more of a challenging one. How the rate of deceleration? Well, it's interesting in the question. What it says is, well, let's draw a VT diagram of this. It says the lift accelerates for 2 seconds and then stays at constant speed for 10, and then they just remove drive from the motor and allow it to coast. So it's got some inertia and it wants us to carry on to stop. So how far, so what's the rate of deceleration? Well, let's just think about a VT diagram here. It's going to look something like this, isn't it? It's going, so we've got this, and we know it does 2 seconds to start with and gets up to 4 rads per second. It then stays at 4 rads per second for 10 seconds, so that takes us to 12, and then it coasts to an unknown time, 0, and the only thing making it carry on is the inertia of all the objects. Well, let's think about what so this is part 3. Let's think about what objects we've got here and the net force difference. Well, the net force difference, we can do this as an equation, because acceleration is going to be equal to the force divided by, we'll call it mass stroke inertia. So the net force difference is going to be equal to the force of the 1200 kilos pulling down now remember, at this stage along here, look, coming across this part, I'll draw it in blue, across here we're at constant speed, therefore there's no acceleration problems. We've only got 9.81 gravity pulling down, but what's affecting it the other way is take away the 1000 kilos the other side of the pulley, So that's the net forces on the pulley, because the motor's not running. We've only got those forces pulling either way, divided by the inertia, the things that want to resist that change. Well, there's a 1200 kilo load. That can't be forgotten about. That's going to take some, that's going to want to carry on moving. It's moving at 4 meters per second. It's going to want to stay moving. It's not, doesn't like changing. There's also a 1000 kilogram force. That's also moving. It's on the same rope. It's going to want to carry on moving. And then we also have the inertia. Now the moment of inertia here is 500. We're already given it, which comes to 0.726. That is meters per second squared. So that's its rate of deceleration due to the inertia of both of the masses, these two masses here, and also the inertia of this wheel wanting to carry on spinning. And that together means that it doesn't stop immediately or stop just with gravity. It actually wants to carry on going because it's got this inertia in there. So that's its rate of deceleration. Now the next part of the question, the last part, was the distance moved by the lift during its total journey. Well, let's go back to our free body diagram here. I'll draw it a bit bigger. So we know this to be 4 meters per second velocity, this to be 2, and we know the rate of deceleration here is, so we could work out time if we wanted to, because we know from SUVAT that V equals U plus AT. Therefore T, the time, is going to be equal to V minus U over, which equals 4 over 0.7266 equals 4 over 0.726667, 5.5 seconds, which takes us to 17 point. Well, this first bit is, so we've got 4 here, 4 there with this triangle here, section 1, is going to be 4 times 2 times a half, which is going to be equal to 4. This rectangle in the center here, I'll draw it in blue to show it here. This is going to be equal to 4 or meters per second multiplied by 10, so 40 meters. And then this last section is going to be equal to 5.5 times 4 times a half, because it's a triangle, and that's equal to 11 meters. Now if we add all these up, total distance S equals 55 meters.